As the concept of Bayesian Sparsification of a neural net. So, welcome.
Thank you for the introduction. Hello, everybody. My name is Nadezhda Chirkova. I work at the Bayesian Methods Research Group, led by Professor Dmitry Vetrov. We are located in Moscow, Russia. And today I will give a tutorial on Bayesian Sparsification of neural networks. This area of research was actively investigated during last several years. And today I will talk about papers that were and the work that was done in the research group of Professor Max Wellin in Amsterdam, some of them from our research group and of course from other research groups. So at the bottom of the slide I will often put a link to the paper this slide is based on, so you can later check these papers if you're interested. So this is our plan. Firstly, we will talk about sparsification and why it is important. Then I will remind you about Bayesian neural networks. I think you already know the majority of the material from this section, but we will look at it from neural network perspective. And also it's useful to establish my notation because it may differ somehow from the notation of the previous days. Then we will talk about sparse variational dropout in details. It's a particular model that is quite popular nowadays to solve the task of sparsification. After that, you will implement this model, sparse variational dropout. And finally, when you already understand well this model, we will talk about some follow-ups to SparseVD and some other models as well. So now let's start with the introduction. As all you know, deep learning achieved very good results in many tasks like image classification, image segmentation, natural language processing, video understanding, and so on. And it is a well-known empirical fact that model quality usually scales with model and dataset size. So if you take more data or use a model with bigger number of parameters, you usually obtain better quality. And state-of-the-art models usually incorporate tens of millions of parameters now. But when you are thinking about the deploying of your model for production, your resources may be limited. So assume, for example, you are developing a deep learning model, or for example for image classification, that will work on user's smartphone. So it will not on smartphone, not in the cloud, but on the smartphone. In this case, your memory is very limited. And if your network has a size of hundreds of megabytes, the user will not be happy with your application. And the same with, for example, smartwatches, even more limitations on network size, and all other smart devices. And even if you process the user's request in the cloud, the time for your reply is usually very limited. So you must reply like in milliseconds. So the system should be very fast. Okay, so we have an urgent industrial problem of training compact and fast neural networks. So it's a problem of compression and speed up. In this tutorial, we will focus on compression, but as we will see later, compression often entails speed up too. And why we are talking about this problem here at this summer school, it's because this problem is well solved using Bayesian framework, specifically Bayesian neural networks. And we like all the Bayesian stuff here. The methods for neural network compression are usually divided into three groups. The first is quantization, when you when you store the weight of your matrix, of your network, in low precision format, or even in binary, for example. But since you have a lot of such low precision weights, your model performs quite well still. The second group is matrix factorizations, when you decompose your weight matrix into a product of two or more low-rank weight matrices. That's how you compress your network. And the third group is sparsification, when you train sparse weight matrices, so you set a lot of weights in your network to 0. And this is what we are going to focus on. So about sparsification, assume you have some neural network. On the left you see the weight matrix. On the right it is computational graph. So it is another representation of our neural network. And when we sparsify it, we actually set a lot of weights to 0. So our weight matrix becomes sparse. And in terms of computational graph, it means that we zero out, like we remove connections between neurons. And here I would like to notice that our goal is to obtain the sparse model at the end of training. So it doesn't matter how we do that. We can gradually sparsify the network during training, or we can just once sparsify it after training. It doesn't matter. So our goal is a sparse model at the end of training for production or for prediction stage. And there is an important subtype of sparsity called structure sparsity. So here on the right, you see some crossed neurons. Why are they crossed? It's because we set to 0, we remove all the outgoing connections from these neurons. So in terms of the weight matrix, it means that we zero out a column in the weight matrix. And in this case, actually, the output of your neuron, because there are no outgoing connections, the output of the neuron is always multiplied by 0. So in other words, this neuron does not affect the network output. It's like useless neuron in the network, and we can remove it. So it is called structure sparsity because you introduce some structure in your weight matrix. In our example, it's a column. This structure is represented by columns of the weight matrix. And in this case, you can actually make width of your network smaller. And it leads to more efficient compression because previously we stored our weights in sparse matrix. It was our compression. Here we reduce the width, it's even better compression. But also it speeds up your forward pass because you have less neurons at each level. That's why I said earlier that that sparsification often entails speed up. So our goal is sparsification of neural networks. The benefits are that you obtain sparse matrix, so it's less memory consumption. If we do structure sparsification, we have faster testing stage or prediction stage. Also, sparsification provides some regularization because the network, the sparse network has less degrees of freedom than dense network. And also sparse models are usually assumed to be more interpretable. So for example, when you have sparse weight matrices, like for first layer, you will have your feature importances of the input features when computing the hidden neurons from the first layer. It's like more interpretable maybe. Of course, there are some drawbacks. There is no free lunch. Okay, at this school there is free lunch actually, but generally in our life there is no free lunch. And this drawback is that usually sparsification leads to some small quality drop. It's not always, sometimes it's possible to train sparse model without quality drop, but usually we obtain some quality drop. And the applications include mobile devices, smartphone, online services, as we discussed earlier. So does everybody understand our problem now? If not, let's repeat something. Okay, great. We will talk about Bayesian Sparsification, but of course there are other approaches. And the most popular, the second popular one is pruning, or also called magnetic pruning. Let's discuss it because it's quite simple heuristic algorithm. So how pruning is defined? We just modify a bit our training algorithm. So to induce sparsity, we add some regularization. Most popular is L1 regularization. And for example, at the beginning of each training epoch, you set to 0 all the weights whose absolute value is less than predefined threshold. So it's actually a very simple algorithm, and it is like one of examples. It works. But there are a lot of other approaches of this type. So there are a lot of papers on that. They differ in different things. So for example, you can prune not based on the threshold, but set to 0 some fixed proportion of weights in your neural network or in your layer. Also, you can choose different threshold shadows. For example, increase threshold gradually or use constant threshold. You can decide whether to propagate gradients through zero weights or not. Also, the popular framework is firstly to train, then prune for several epochs, and after then retrain again. It usually makes the model to work better. But all these variants produce a very huge number of hyperparameters that you have to tune if you want to use such approach for your particular task. So here is like quick comparison of two. These are really two popular approaches for sparsification. So in Pruning we have a lot of method hyperparameters. In Bayesian Sparsification we have almost no hyperparameters, but if you want you can induce them actually. You need to choose training shadow in both frameworks, of course, because it's like we are training our networks with SGD usually. We have to choose its hyperparameters in any model. And of course, one of the advantages of Bayesian Sparsification is that it's Bayesian, and we like all the Bayesian things. So now that's all for the introduction. Let's now turn to Bayesian neural networks. And again, you know this material, but it will be like an overview, and also we will establish our notation. So, Bayesian deep learning, as you maybe noticed, the first 3 days of the school were devoted to classical Bayesian methods and probabilistic modeling, and the last 2 days are devoted to Bayesian deep learning, or a combination of deep and probabilistic paradigms, because both these paradigms are successful in data analysis. And generally speaking, Bayesian deep learning can be divided into these two groups. So you have something probabilistic and some neural network. How to combine them? The first option, you plug your neural network inside the probabilistic model of your data. In this case, we come to deep generative models. For example, variational autoencoders, normalizing flows that we discussed yesterday and today. And the second option is reverse, when you make the weights of your neural network probabilistic, stochastic. In this case, we come to Bayesian neural networks. They are usually discriminative. So this model is quite similar to Bayesian linear regression, but here we have nonlinear prediction function. And your discriminative model is just any usual neural network, for example, for classification, but with stochastic weights. Bayesian neural networks are actually regularized neural networks, but regularized in a specific way. The traditional regularization we all know is that we add some regularization term to our data loss. Usually it's like L1 or 2 regularization. But for neural networks, another type of regularization usually performs well. It's regularization by noise. And in this case, our objective is an expectation over the noise of our data loss. And the examples here are data augmentation, dropout, gradient noise, for example, in Benjamin dynamics, and so on. And Bayesian framework provides a principled approach to training with noise. Let's see how. So here we have like comparison between deterministic and Bayesian neural networks. In deterministic neural networks, we find during training we find point estimate for the weights given our data and optimizing some criteria. And at the prediction function, we have this discriminative model and use our point estimate to make predictions. And here X star is our new testing object, and Y star is the prediction for this testing object. What happens in Bayesian neural networks? Here, our weights are assumed to be stochastic. So we introduce some probability, some probabilistic distribution for these weights. And the input to our training procedure is not only the data, but also the prior distribution over the weights that actually encodes our prior information, our desired property about the weights. And our training, also called Bayesian inference, is that we find a posterior distribution over the weights. And then we use this posterior distribution on the prediction stage and integrate over it to obtain predictions for our new object x star. And this discriminative model, Py given x and w, is just a neural network. Okay, so why go with Bayesian? Why should we use Bayesian neural networks instead of just usual deterministic neural networks? Okay, so there are a lot of reasons we discussed at this school. Let's just quickly go through all of them. So first is regularization, and we discussed it a few slides earlier. The second is ensembling. So a Bayesian neural network is actually an infinite ensemble of neural network. So here, to make a predictions for new object x star, given our training data set x and y, large x and y, we integrate out our weights with this our posterior distribution. And we approximate this integral with Monte Carlo sampling, so we can use many samples from our posterior. And actually, it means that we average softmax outputs across several samples of the weights. And this is the graph. Here on the x-axis is the number of weight samples. On the y-axis is test accuracy. We see that the test accuracy grows at the beginning, but it quickly saturates. So, for example, 20 samples would be enough to obtaining good quality, and these are results for MD testing. But okay, so accuracy quickly saturates, but the negative log likelihood for the test sample keeps improving, and that's important because this negative log likelihood is a measure of uncertainty. So assume we have a neural network. Usually it remembers all the labels for training set. So on the training set we have 0 error, and of course our network is very confident. But for the test set, we usually have the network's accuracy is usually not 100%, so it makes some mistakes. And if our network is overconfident for testing stage, then its test negative log likelihood or cross entropy will be very high, negative cross entropy. So the test negative log likelihood is like the measure of uncertainty, and this quality measure is used usually in the papers to measure it actually. And we see that this test NLL keeps improving when we take more samples. So Bayesian neural networks are good for estimating uncertainty. And here is another example showing that Bayesian neural networks are better in estimating uncertainty. It's taken from this paper by Loizos and Welling about multiplication normalizing flows. Here the left graph stands for deterministic network and the right graph stands for Bayesian neural network. And on the x-axis we see the rotating digit 3. So the left 3 is like normal 3, on the right we see like rotated abnormal 3. And on y-axis there are 10 probabilities assigned by our network to this input. And for left 3, we want to obtain like confident result, and we usually obtain it because it's actually 3. And for the right 3, we want to have something like uniform distribution, as was discussed yesterday in Alexander Huben's talk. And for deterministic network here, we see like also overconfident network, overconfident predictions. And on the right, for Bayesian neural network, for rotated 3, that is not normal. Of course, yes, okay, it's not uniform, but it's much more uniform than on the left. So Bayesian neural networks are really good in estimating uncertainty. Okay, not really good, but maybe a lot better than deterministic networks. The next advantage of Bayesian neural networks is model selection. So you can choose the prior that has its own parameters. Then we can call them hyperparameters. And if we optimize with respect to these prior parameters, it's called empirical bias. We can treat it like we automatically choose hyperparameters. And we will discuss it later in an example, but really later. The next advantage is easy online learning. So in some tasks, your data comes gradually in independent parts. So you firstly obtain dataset D1, train on it, and forget it. You just have your model. Then you obtain a dataset D2, train on it. Of course, you want your network to perform well on both datasets D1 and D2. However, you are now not training on D1. And so on. So D3 comes, we throw away D1, D2, but have our model, train on them, and continue it. How it can be done in Bayesian framework? So firstly, we use our usual prior PW to find the posterior distribution. And when the second data set comes, D2, we can use this posterior from the D1 as a prior for the next model. So we just plug this first posterior as a prior for the next model. And since we have this denominator in both numerator and denominator, so it just cancels, so we can just insert the likelihood multiplied by prime. And using these sequential updates, we can find PW conditional D when our data set comes gradually. So it's easier online learning. Okay, that's all for the advantages of Bayesian neural networks. Let's recall how they're usually trained. So as we said, we want to find the posterior distribution over the weights. However, in neural networks, posterior distribution is usually intractable. So we approximate it with some parametric distribution, Q. It has parameters lambda. And to find this approximate posterior, we minimize the CAD divergence between approximate posterior and true posterior. And of course, this CAD divergence, we cannot compute this CAD divergence. But this task is equivalent to optimizing evidence lower bound. You have derived it many times. And here we have data term on the left and the regularizer on the right. And this regularizer actually says that our approximate posterior distribution should be like somehow close to the prior distribution. Remember, we have like two types of Bayesian deep learning. And the variational autoencoders were discussed a lot here. And variational autoencoders are usually also trained using variational inference. Okay, not always, but usually, but often. And there is also evidence lower bound in that model. So compared to variational autoencoders, in Bayesian neural networks, there are two main specifics. First is that our CAD term is global. So in variational autoencoders, our CAD divergence factorizes over objects, training objects, and here it is global because weights are global for our network. And the second is that we have extremely high dimensional approximate posterior that we have to deal with. Okay, so we now discuss the general framework for Bayesian neural networks. And if you want to specify the particular method for Bayesian neural networks, we have to choose several things. Firstly, we have to specify our prior to establish our model. And then we need to decide how to train our model. So firstly, we need to choose particular family for approximate posterior distribution. And also find answers for two questions. So how to compute the CAD divergence and how to estimate the expectation. And now we will go through these 4 steps for our model called sparse variational dropout. Any questions at this point? Great, because I think it was easier for you. You already know it. So now we are turning to the third section of our tutorial devoted to sparse variational dropout. Here I would like to make 2 notes. The first note is that, of course, there are other specification models, Bayesian models. We just focus on this one because it's quite popular. And the second note is that this tutorial is more about how to train Bayesian neural networks in practice. And we will see that it's not only about math, but it's also about some engineering. because we are training our networks on computer. And we will not have a lot of derivations, but we will have a lot of, some number of tricks needed to train Bayesian neural networks. So we will discuss like how to train them in practice. This is the visualization of how sparse variational dropout works. And I put this slide here for 3 reasons. Firstly, because it's a GIF image and it's funny. Secondly, because I want to remind you our problem, that we are going to sparsify neural networks, so to obtain sparse weight matrices at the end. And the third reason is that if you are already sleeping, I suggest you to wake up at this point, because we are now turning to the main part of our tutorial, and we will need to implement this model later. And about these pictures, here we see our weight matrices. So white stays for 0 weights, red stays for positive, blue for negative weights, and we see that at the end we obtain like 270 compression from this data set, which is a quite good result. Okay, so let's go on. And our first checkpoint is choosing prior distribution. So in sparse VD, the log uniform prior distribution is used. Its probability is proportional to 1 divided by the absolute value of your weight. And you see the visualization of this prior distribution on the graph. So why do they choose it? Because you can choose many priors. So firstly, this prior is concentrated near 0. It's what we want. We want at the end to have a lot of 0 weights. So we put a lot of probabilistic mass near 0. But there are other distributions with this property. Actually, this prior distribution promotes removing very noisy weights. So of course, all our weights have some noise, but there are very, very noisy weights. And this distribution promotes removing these noisy weights. And why are very noisy weights bad? Because they can correct your predictions, correct your data wrong. But we will discuss why it happens a few slides later. Okay, so we chose the prior distribution. Now, our second checkpoint is how we will approximate our posterior, our intractable true posterior. And here is quite a simple choice. We just choose normal distribution with learnable mean and variance. And if we do reparameterization trick for this distribution, we see that this is equivalent to just taking usual weights and adding some noise. So here epsilon is noise, mu is the mean, and sigma is like standard deviation. And it is equivalent to just taking usual neural network, adding some noise to its weights, and that's all. And okay, we learn the standard deviation or variance of these weights. So it's like very simple approximate posterior distribution. But actually, it's not the only way to parameterize this approximate posterior distribution. So for example, we can choose another parameterization, and this parameterization was used in the original paper about variational dropout, not sparse, but variational dropout. They used this parameterization, they needed actually this parameterization. So here we just replace sigma with alpha multiplied by mu squared. So our approximate posterior stays the same. These are two equivalent models. Because for each sigma you can compute alpha, for each alpha you can compute sigma. But this parameterization actually leads to another noise. So here we perform the parameterization trick again, and see that if previously, let's return, we had additive noise for weights, 0-centered additive noise. So here we have 1-centered multiplicative noise. So it's the same distribution, but another parameterization. But okay, looks good, why not to use it? But let's check the gradients. So when we will train our network, we will have to compute the gradients of ELBO with respect to mean values. And if we do it with multiplicative noise, with the second parameterization, You see it on the left. What we obtain here, dl by d mu equals, we are just applying chain rule. So the first term, dl by dv hat, stays the same for both parameterizations, and the second term differs. So let's compute the second term for the multiplicative noise on the left. So here our weight is just mu multiplied by the bracket, and this bracket is actually the derivative. But if we look at it, we see that it's actually very noisy if alpha goes to large values. So if alpha is large, then our multiplicative term is like very, very noisy. And in sparse neural networks, we will have large alphas. So it's very inconsistent parameterization, and it's really hard to train. So if we will have such noisy gradients, our training process can even diverge, or at least it will train a long, long time. But let's see what happens if we use another parameterization, just simple plain parameterization with mu and sigma, just mean and variance. It's actually okay with that, because here the derivative of p hat with respect to mu is just 1, no noise, perfect gradients. So why I put it here is that point about engineering. So since we are training our neural networks on the computer with stochastic methods, optimization methods, we need to think about such things. So for example, here parameterization matters, the same distribution but different parameterization. Okay, so now we have approximate posterior. And now let's turn to the third checkpoint. It's Kyle divergence. Our Kyle divergence is a Kyle divergence between normal distribution and log uniform distribution. So it's regularizer between approximate posterior and prior, so normal and log uniform. It's actually intractable analytically, unfortunately. But in this paper, Variational dropout and the local reparameterization trick, it was proved that with this log uniform prior distribution, the Kyle divergence depends only on the ratio of sigma to mu, not on them separately, but on the ratio. And we will denote this ratio with alpha. Okay, we already denoted this with alpha on the previous slide. And actually, this log uniform distribution is the only distribution that satisfies this. So a Kyle divergence depends only on their ratio. Why it is good? Because let's look at the here we have visualization of this Kyle divergence. We will talk how it is obtained. We see that this Kyle divergence, we maximize this function. It actually favors big alphas because for big alphas we have this plateau, and on the left we have something close to linear function. So this Kyle divergence favors large alphas. And what does large alpha mean? It means that our sigma to mu is also large. So you have a weight with some mu, with some mean value, but very big variance. That is what I called earlier very noisy weights. So these weights are actually useless because they corrupt prediction, corrupt data term. We don't want to have these weights, and actually we will sparsify them. Not we, but training process. Because if we have these big alphas, it's called signal to noise ratio. Big this ratio, then mean values automatically go to 0, because it's for network it's bad if they are not 0. So if we have large alphas, our training process moves mu close to 0. So we end up in sparse model. Okay, but we didn't complete our part about how to compute this Kyle divergence. We discussed why it is good for sparsification, but how to compute it. Actually, it is intractable. So now we know that this depends only on the ratio of sigma to mu. We cannot compute what can we do? The obvious answer is sample. Every time we cannot trace something, we can sample it. Yes, but we can do something better. So we will start with something. A good thing here is that the Kyle divergence is a function depending on only one value, alpha. So it's one-dimensional function actually. And we can sample a lot of points. and you see there like black points on the graph. We have these black points, we sample, and actually after that, what was done in both two papers is that they approximate this one-dimensional function. So you just sample and then you look at the graph and say, I think it's that function. I don't know how they did it, because it's not so trivial task as it looks. But they did it actually, and their approximation shown on the right from this second paper, it has about it has an error about 10 and minus 8 degrees, so very, very small error. It's like very close analytical approximation. And it is possible, again, because our L divergence depends only on one value, not 2 mu and sigma, but on 1, on alpha. So okay, we have now approximation. Now our L divergence is just a function we need to compute during training, and that's very good. And again, it's about engineering, because you have this some theoretical stuff, and you need to know how to deal with it in practice. Okay, now let's move on. And we have the fourth question remaining. It's about how to compute the estimation, our data term in ELBO. So I remind you that it is evidence lower bound. We already know what to do with the right term, it's class divergence. Now we need to choose what to do with the left term. And you already know the answer because we discussed it, for example, yesterday in Alexander's talk. It's called double stochastic rational inference. So first problem, we have sum here, sum of the training objects, and we can have a lot of training objects. And we deal with as with any other such functional. We just replace this sum with sum over a mini batch. So we just sample a mini batch and perform stochastic gradient descent. It's first stochasticity. Then inside this sum we have this expectation that is intractable because py given x and w is a neural network. And here we of course sample weights from the approximate posterior distribution. So we sample twice, that's why it's called double stochastic rational inference. Okay, so now that we know that we will sample weights from Q, and here we need bit more tricks. So of course the obvious thing is that we want to obtain unbiased estimates of the gradient, and to obtain it we need to use reparameterization trick. It's good that it works here because we have normal approximate posterior, fully factorized by the way. So we just reparameterize it like mu plus epsilon multiplied by sigma as we done earlier. Okay, but now let's now remind that, recall that our posterior is very high dimensional. And actually we have this expectation for each object in a dataset or in a mini batch. So if we will sample weights per object, it will be really too expensive. Because you have square weight matrices, and you have to sample these weight matrices for each object in a mini batch. So it's like 3D noise tensor. It's very expensive and it's very slow. I tried it. It's really slow. It's too expensive. What can we do? The obvious answer is like, okay, maybe sample weights per mini batch, not per object, but per mini batch. So we just share weights between objects. It's heuristic, but why not? We can do it, it will work, but it is like not so good because in this case we obtain high variance of stochastic gradients. And as we discussed earlier, it's not so good to have high variance of stochastic gradients because in this case we have very slow training or even divergence. And in this paper about variational dropout and the local representation trick, this trick was introduced, how we can solve this problem. It's called local representation trick. Let's first discuss what it is, and then we will see why it helps to overcome the problem of large variance of stochastic gradients. So let's firstly look at the left part. As we remember, our weights are from normal distribution, each weight from each individual normal distribution. And our, for example, fully connected layer is like matrix multiplication. So here A is the input matrix, B is the output matrix, and W is our weights. And actually, each element of B is a linear combination of normal random variables with like constant weights. Because A is constant, W is normal, and there is the property of normal distribution, and the sum of normal distribution is normal. If you multiply the distribution by a constant, it's also normal, and so on. So actually, each component in B is normal. And we know its parameters. So let's now look at the right part. We can compute the parameters of this B actually, because it's just linear combination of normal distributions. So the mean will be like A multiplied by mu, and the variance of B will be like that. Here blue means element-wise multiplication. So here we have element-wise square for the matrix and for the second matrix. And then matrix multiplication. So now we know that our pre-activation, I call B pre-activation, our pre-activation is normal. And we can sample this pre-activation instead of sampling weights. And in this case, we will need like two-dimensional noise, not three-dimensional. And it is good. This is how local reparameterization trick works. We just apply the reparameterization to this second row and end up with third row. So our B is just A mu plus this expression, and there is noise epsilon, and this noise is just a noise per object. Okay, let's now discuss why it is good. So our predictions, first case, we use one weight sample for a mini-batch. In this case, since we use one weight sample, our predictions have high correlation. So we just share one weight sample between objects, so the predictions are correlated, of course. So there is correlation. If we use the local reparameterization trick, we do not share anything between objects in a mini-batch, so the predictions are not correlated. And why does correlation matter? You remember that property from probabilistic theory that if we have a sum of random variables and we want to compute the variance of this sum, then this variance is composed of two terms. The first term is variance, their individual variances, and the second term is their pairwise covariances. So if the random variables are not correlated, our variance becomes smaller. If they are correlated, it becomes higher. Here they are not correlated, so the variance is lower, and that's very good. So local reparameterization trick helps to make the variance of stochastic gradients lower, and it is an effect of using a mini-batch, how to deal with the mini-batch of the objects. So this is the first positive thing about the local reparameterization trick we will use in our model. But the local reparameterization trick also reduces the variance of the stochastic gradients with respect to sigma for one object. So previously it was for a mini-batch, here it's for one object. I'm not going to write this formula. The proof takes about 1 page in the appendix in this paper. You can check it if you are very interested. It's just a sketch. So here we take our ELBO, take derivatives with respect to sigma, and try to find its variance. The variance actually decomposes into two terms. And the first term is the same for both parameterizations, and the second term is not. So for local reparameterization trick, this second term vanishes because, remember, each component of pre-activation, B, is like something plus something times epsilon. And there is individual epsilon for each B component. So there is one-to-one correspondence between epsilon, dotted zeta here, between epsilon and B. So if we have B, we can compute zeta if dots are fixed, and vice versa. So this second term vanishes because given B, and you see the conditioning on B here, given B, the noise is determined unique. And for RT, for reparameterization trick, it's not the case. So for reparameterization trick, we have positive term here, so the variance is large. One more thing, it's about how to use RT for convolutions. because in convolutional neural network, B, our output of the layer, no longer factorizes over inputs, over spatial positions, because same weight samples should be used for different spatial positions. It's quite a problem. Does the animation work? No. It works. Great. But in convolutions we have to use one weight sample. So assume we have like one input image, fix one filter, and apply this filter to each image. We have to use one filter for each spatial position. It's the definition of the convolution. So in this case, our positions in our output image will be correlated. It will be normal but correlated because we have like use normal weights but the same normal filter for each spatial position. So they will be correlated, and to do exact local reparameterization, we have to estimate the full covariance for each activation. It's expensive. What we usually do in such situations, we just do mean field approximation. So we say, okay, let's assume that they are not correlated, that our covariance matrix is just diagonal, and then we end up with this easy formula. So it looks like pretty the same as for fully connected layers. So it's like A convolved with mu and something very similar to convolution to fully connected layers. And actually, this mean field approximation performs better than sampling weights for an image.
Question or remark, just to show I understand intuitively. This works because also they are probabilistic and you learn them. But like if they were probabilistic and you were to drop
the second term.
randomness, then
I'm not sure I understood the question well, but it sounds reasonable. Okay, so for now we discussed all 4 questions. We decided to use log uniform distribution to approximate the posterior with normal distribution. We now have analytical approximation for the KL divergence and use reparameterization trick and local reparameterization trick to estimate the expectation. And we discussed actually several tricks that are needed to train Bayesian neural networks. We still have some parameters in our network that are not generally weights, for example, biases or patch norm parameters. This is a very simple thing we can do with them. We just condition on them and optimize with respect to them. So we treat such parameters as deterministic values. It's very simple. It eventually assumes that a flat prior and the delta peak posterior. It's okay if we just, so if we need to train some more values that are not stochastic but deterministic, we just plug them into our formula and do it. So it's not a problem. And by the way, I didn't mention earlier one more thing, one more small trick, is that here we optimize with respect to mu and log sigma, not plain sigma. Why? Because first, if we need sigma to be positive, and if we optimize with respect to log sigma, we will end up in always positive sigma. And the second reason is that in this case, we will search for sigma in logarithmic scale. That's a good solution for variances, and it is as it usually done. Okay, so now we are ready to describe our final algorithm. Actually, if we do not use local reparameterization trick, the algorithm is very simple. It's like your usual tracking of neural networks, but with sampling weights. So the first step is just you just sample noise and add it to your weights in the neural network. Then you perform usual forward pass, and then perform backward pass. And actually, what is our criteria? It is our loss function, because if this py given x and w is usually cross entropy, it's like very common loss. And also we have some sparse regularizer We have analytical formula for it, so it's just a regular answer. And we do backpropagation for mu, log sigma, and beta here. So actually, it's a very simple algorithm for training. We used a lot of tricks, we had quite a complex probabilistic model, but finally we obtained like very simple algorithm. This is an illustration how forward pass with stochastic weights works. To tell the truth, I just put this slide here because there is a cat on the slide. So here we take the input image, we use some noisy weights, so we add noise to the weights, convolve it or multiply, then pass to the activation function, and that's all. So very easy thing. But we actually need to use LRT, but it doesn't complicate things so much, so we just, instead of like, this is without LRT, this with LRT, so here we sample noise for weights, here we just sample noise for pre-activations and perform forward pass with LRT, but it modifies our forward pass just a bit. So it's again very simple algorithm for training our neural network. But thing to note here is that we have like two parameters for each weight. It's mu and log sigma, not just plain weight as usual. Okay, now let's recap that we are talking about sparsification. We discussed that our log uniform distribution and our divergence leads to sparse solution. But at some point we need to like obtain this sparse solution, and this is that point. So after training, we just perform pruning or sparsification, and usually it is done on the base of this ratio. We discussed that we optimize this ratio during training, so why not to use it as a criteria for sparsification? We just take this ratio, it's mu to sigma, so it's mean divided by standard deviation of your weight. And if standard deviation is much more than the mean, then we have very noisy weight, we just remove it. Remember our thoughts about it. So here we just have this ratio. If it is less than the predefined threshold, we just set this, it should be mu here, sorry, this weights to 0. This ratio is called signal to noise ratio, like mu is signal, sigma is noise. And about this threshold, usually like constant threshold about 0.05 is used. It works in almost all applications, and it was used in the original paper about sparsity. If you want, you may tune it as well. But compared to pruning, tuning threshold here is very simple, because actually we don't need this threshold during training. We just use it after training to prune our model. So if you want to tune it somehow, it will be very cheap. Just after training, you try different thresholds, compute the accuracy for them, and select like the threshold that satisfies you. Okay. And what we do at the prediction stage, so now we have sparse model with a lot of zero weights. Again, mu should be here. We have now a new batch, new mini batch X. What we do, here usually we just use mean values of the weights. So we do not do ensampling in sparse models usually. That's because we want most compact and fastest network. And yesterday Alexander actually gave a talk on combining these two things, sparsification and uncertainty estimation, and we have seen that it may be not so simple as it looks like. But in sparsification we usually use like mean values of the weights, and it actually works.
Question.
Mm-hmm.
Did you experiment with actually trying and sampling and seeing how much you benefit from it?
I think we experimented. Usually it's not very good quality if you just sample one sample, but comparing between sample, for example, 10 samples, and this using these mu values is quite the same. So this is our model. We will implement it in like 10 minutes. But now a few more words. Here I just want to show you quickly another model with another prior, but this model actually leads to a very similar model, very similar method for training. And it's called automatic relevance determination. Maybe you remember that we had a slide about empirical Bayes, when we have parameters in our prior distribution, and when we optimize with respect to them, we can treat it like automatically tuning hyperparameters. And this is an example of such a model. So let's just use another model. We take this normal prior with learnable variances for each weight. Something like here. We denote this variance with inverse tau. Now we again need to compute the KL divergence. But here it's simple, because this is KL divergence between two normal distributions, the approximate, posterior, and prior, both fully factorized. So we just compute it analytically and obtain this formula. And now we will need to optimize our evidence level bound with respect to mu and sigma biases, as usually, but also with respect to tau, because now we have parameters in our prior distribution. And actually, this tau does not participate in data term. Because prior distribution does not participate in data term on the approximate posterior. And we have this tau only here, in this KL divergence. And actually, if we optimize this expression with respect to tau, we obtain like very simple solution. It's in dotted frame. So we optimize that expression with respect to tau, obtain this formula, put it into the expression for the KL divergence, and obtain this expression. And then we rearrange terms. So this is another model. Here we have prior with learnable parameters, but we can optimize analytically with respect to them and obtain this KL divergence. Let's now compare two models. So in sparsity we use log uniform prior. In IRD we use normal prior with learnable variances. And we have these two KL divergences. And actually, this term, blue term, is the same in both parameterization, in both models. In the first model, there is also this first term with coefficients and sigmoid. But actually, this is bounded term that does not affect too much. Of course, it affects, but not too much because it's bounded. And the second term is like not bounded. So in practice, these two models usually work quite the same. And of course, all the training procedure, like approximate posterior tricks, stay the same because we just chose another prior, and the training is the same for both models. So now quickly about the results of this model, variational dropout. Again, this picture with the huge compression for MNIST dataset for convolutional and fully connected networks. These are results in tables. So here are experiments for fully connected and convolutional network again. The first row in each block of the table is the quality of the dense model. The last row is sparsity model, and in the middle there are some baselines. And we see that for fully connected network, there is some quality drop in sparsity, but sparsity compresses this network a lot. And other classification methods cannot compress it for such big number, compression ratio. With convolutional neural network, sparsity leads to the best quality and best compression here. So here we do not have quality drop, we even have quality improvement. It is like because of regularization effect. Also, in the paper, there are experiments on BGG-like architecture for CFR10. So here in the graph, the solid lines is error, dotted line, dashed line is sparsification, and on the x-axis, they vary the width of the network, so they just multiply the number of the neurons by k. And we see that, of course, the error is lower for larger k, and the compression is also bigger for larger k, because like number of ways needed to solve the problem is usually approximately the same, but the starting network with big k is bigger. And also we see that with high compression, the quality of the sparsity is the same as the quality of the baseline, so there is no quality drop. Although on the left there is small quality drop. And also there is an interesting experiment with random labeling. Probably you heard about this thing, that if you take usual deterministic neural network and take a data set and just permute all the labels. So there is no dependence between data and labels, you just permute them. It's like random label for each image. And for deterministic network, you can actually overfit it so that it remembers all the labels, if the network is of enough size. So you see it in the first and the third row, the deterministic network, FC plus like binary dropout, achieves 100% train accuracy on this permuted task. Of course, the test accuracy is not 100 because like, there is no dependence between images and labels. And the Bayesian neural network, our sparse variational dropout, it actually removes all the weights, sets all the weights to 0, and returns empty network. And it's like an illustration of the effect of using sparsified Bayesian neural networks. Okay, now we are ready to turn to the practical assignment. You can use this QR code, and also I posted the link to WhatsApp to this assignment. So please just listen to me for 2 more minutes. I will just show what you have there, and then you will have enough time to solve the assignment. So the assignment actually consists of first part is when you just run the code. It is an example of training fully connected network for MNIST in PyTorch. It's just in case you are not familiar with PyTorch so well. If you are familiar, you just skip it because these cells are already run. And then you actually need to implement 2 classes, the layer, fully connected layer, and the loss, and then run the model. And then perform some analysis of the model. I will try to switch to it, to this task. Yes, I can do it. Do you see? No, you don't see. Okay. Let's try again. Yes, very good. Maybe I can even use this thing here. No? Okay. So this is practical assignment of sparse variational dropout. You will train actually a fully connected network for a MNIST dataset. So here you do needed imports. If you can run it in Colab, I think you already run something in Colab in school. So just use these lines to install PyTorch and Torch Vision. Please download the logger. It is in the same repository repo as this tutorial. Also some imports. So this is the illustration how we just train simple network in PyTorch. We first load the data set, then we define our network. We have here 2 layers. So in initialization, we just define all the necessary stuff. In forward and in forward function, we actually perform forward pass. Then we define a device where to store everything on GPU or on CPU and create an instance of our model. Then we define a loss, then we define optimizer, then we create logger instance and define the training procedure. Here is some code. This stuff is needed for specification, just don't watch it right now. And training is actually very simple, so you iterate over the training batches, move each batch to the CPU or GPU, perform forward pass, backward pass, and also compute metrics, its loss and accuracy. And the same at each epoch with the testing data set, but you don't perform backward pass here. So this is your training procedure. We just run this train and obtain like 98 test accuracy at the end. And it somehow fits a bit. Also, Also, there is a PyTorch cheat sheet because you will implement the algorithm yourself. Maybe you are not so familiar with PyTorch operations or syntax. So here I put like all the necessary components of the model. If you don't remember how to do something in PyTorch, just watch here and you will find the solution, I hope. I hope I included everything needed here. Or if not, please Google it. This is quick description of our model. This is what we optimize, our posterior, prior, KL divergence. You will need to implement this KL divergence actually, and some more details on the model. So to implement the sparsity model, you need to modify two layers. The first one is fully connected layer, and the second one is loss, because we have some specific loss. So here will be our model. We just replace an n-linear with our linear residual layers, and that's it. And you now need to implement this linear residual layer. There are something like your code should be here. Please fill in the signs. Also, there is scale divergence for each layer. So you need here to like write this formula we had earlier. Then you just run all these cells. Oh, yeah, again, okay. Also, you need to implement the loss. Also, your code should be here. And then you train the model. You just run all these cells and run this cell. So it uses the same training function as we used for deterministic network. After that, you can compute compression ratio and also to do some visualization similar to the visualization of the slides. And actually to look at the actual compression with sparse matrices. And it's like if you are very fast and have time left, these are ideas what to do next. So now I think we have about 50 minutes to do the practical assignment. We will not have a break, but if you need a break, just you can have it. If you have some problems, please raise your hand. I will try to help you. And again, there was a link to the assignment. I think I will try to maybe duplicate them, or you downloaded the assignment already. It's also the link in WhatsApp. Other problems with downloading. Okay, so I just leave it here. I suggest to proceed because we don't have too much time left. Probably I will show the solution, or we again don't have it at the screen, unfortunately. Go ahead, or no, we have it. Here is the solution. Let's take a look at it. Actually, there was a question about constant C in the KL divergence. This constant arrives, I forgot to tell about that, sorry. This constant arrives because our prior distribution is actually improper. So this integral is not, it's like infinite. But we have this, so we have this constant in the KL divergence, but it is constant for all the weights, so it doesn't affect training. So you just set it to 0, forget about it in your implementation. Putting it all together, what we would have is that here in forward class we have our input x. It's correspondence with A in the formulas. Here we have W as mu and log sigma. So what we do when we compute log mean, we just perform usual forward pass. It's like linear layer with weight W and the input x and bias. You can also put here like matrix multiplication, like self W dot x. The similar thing for log STD. So we just have here element-wise squares and also multiplication. Then we sample noise. It will have the same shape as mean and STD. So we just use mu zeros here and apply normal. And finally, we apply our LRT formula. If it is not training, then we compute in our alpha. Log alpha, it's like 2 log sigma minus 2 log absolute value of W. And then we just prune it based on our threshold. and that it is. So we just, and this is our usual linear layer. To compute the K divergence, we again compute alpha, use our coefficients K, and just write our formula here. And finally, when everything is, okay, I again forgot about the loss. In the loss, it's just very simple line. I don't know whether anybody came at this line actually. So here, our data loss is just usual cross entropy. It already encounters for data for batch size. And here we have our K divergence. So this is our loss. It's actually very simple, as was discussed earlier in the final algorithm. Then we train our model, train. And finally, we obtain the model with even better quality than our baseline because of the regularization. And also it's sparsify, quality is here, and it is sparsified a lot, so these are sparsification numbers. Our compression is about 28, which is, or 6, I don't see, so it's quite big. And if you visualize the matrices, you will see like this light pink stays for 0, so there are a lot of zero weights, and on the small portions of non-zero weights. And actually what you can see here is that the weights are like on the lines. So we already have like some sense of structure sparsity, even though we are performing unstructured sparsification here. And these are visualizations when you reshape your layers or your weights. So you take weights, for example, all the weights are going from your image and reshape these weights into image shape and see some interesting like forms here, shapes here. Okay, that's all. Let's return to the presentation because we have some slides left. Now when you, I hope, understand our basic model somehow, if you don't, I suggest you to complete the assignment yourself at home if you are interested, and then compare with the solution. And now we will talk about some follow-ups to this model. And actually we will talk about how to apply this model to RNNs, because it's quite specific. Then how to do structure classification, because it's important in the industry. And third, how does it all work on various data sets and networks. Because as you may be seen, all experiments results were for like MNIST or at least, or at max CFAR10, but does it actually work for large networks in large settings? We will see that. So first about RNNs. Remember this our slide that we had to solve several problems. We chose prior, approximate posterior, and all other things. So now we are working just with another type of network. It's recurrent neural network. The formula will go on the next slide. And it occurs that everything is okay except the last thing. We have some problems there. Let's look at these problems. So firstly, what are the important RNN specifics? So this is the evidence lower bound, but written for the recurrent neural network. It is the same lower bound as earlier. Okay, it's negative lower bound. But here, in recurrent neural networks, as you remember, I hope you remember, the input is a sequence of the arbitrary length. And we process the sequence one by one. And actually, this sequence participates in this likelihood in log py given x. And this results in first important specific is that when we sample our weights, we have to sample all the weights for all sequence because the whole sequence participates in this likelihood. And this was underlined in Gal and Garamani in NIPS 2016. Okay, but it's not enough. If we apply our reparameterization trick and then local reparameterization trick, we will actually see that our T theoretically is not applicable in this model. We will see that in the next slide. And that's, so we should do something with that. And the solution is that, okay, sample one weight for a mini batch. I said it will work. It works. Yes, it works. It results in slower training, but That's it. We cannot use our T here, the local reparameterization trick. And let's see why. So this is, on the top, we have the formula for the recurrent neural networks. So in recurrent networks, we process the input sequence one by one. And at each step, we take input xt plus 1, take the previous hidden state ht, then apply linear layer to that, some activation function, and obtain a new hidden state. So we come from one hidden state to another hidden state, ht to ht plus 1. And here we have two matrices, Vx and Vh. Let's discuss them individually. So the matrix Wh is called hidden to hidden because it connects to ht and ht plus 1. And actually, here our T is not applicable at all. Why? Because you remember the local reparameterization trick relies on the thing that our pre-activation is normal. Because it's like combination of normal random variables with some coefficients. And here these coefficients will be like ht. But look, ht already depends on wh. So ht is not like a constant. It's a random variable depending on the weight wh. So the rule about sum of the normal distribution is not applicable here because actually pre-activation is not normal. So we cannot apply the local reparameterization trick. For the second matrix, Wx, it's called input to hidden. It connects x and h. It's not the case because x here is constant. But here we should remember the first specific of the RNN is that the weights, we should use the same weight sample for the whole input sequence, for all moments of the time. And actually sampling the same noise on weights for all t is not equal to sampling the same noise on pre-activation for all t. So in RNNs, our t is not applicable, but still we can train the model sampling weights per mini-batch. And let's just look at the results. Here there are experiments for text classification on two datasets. The first is IMDb, when it's needed to classify film reviews into positive and negative. And the second is AG News, it's text categorization into 4 topics, 4 categories. And the very simple architecture is used here with the recurrent neural network as a main part. And in 2 blocks, we see the first row is like original dense model, and on the second row is our sparsified model, SparsVD. We see that the compression here is really huge, so it's because tasks are really simple, and the accuracy is either quite the same or even better compared to the original model. And also there is the third row, it's SparsVD VOC. It stands for another modification of the model. We will not dive into details, but it is generally about secure structure specification structure. It's applied to the vocabulary, input vocabulary, because in text classification the input vocabulary is usually very large. So we compress the input vocabulary. We remove unnecessary words from the vocabulary. And it turns out that only a few words, like 300 out of 20,000, are needed to solve the task. I think it's interesting. And let's see at this graph. So here, embedding, because we specified the network, actually structure is still there, even we do not use structure specification for it. And actually the only one embedding component stays in this network. Probably you are not familiar with embedding, just don't worry about it. It's just some value assigned in the network to each vocabulary word embedding. And on the y-axis is just sentiment score computed as a statistic of the data set, like very simple statistic. We take all the text, count number of positive texts, number of negative texts with this word, and renormalize. And actually we see that this learned embedding, the only one, and it is the only one because of sparsification actually, we see that it correlates with like semantics of the words. So on the right there are positive words, beautiful, greatest, amazing, and on the left there are negative words like avoid, poorly, pathetic, worse, and so on. So it's like interpretable model obtained after the sparsification. And also experiments on text generation. Here we see that sparsity work obtains the best results, or sparsity, either one of them. The compression here is not so big because this task is more complex than text classification. And it is language modeling. So in this task, you go through the text, and at each word, you predict the next word. And actually, it can be solved either on the level of characters, so you predict next char, or on the level of words. And on the char level, we see that the vocabulary is not compressed. And it is okay, because we have just 50 characters, 50 letters. Just don't throw them away. And in word level task, we see that only half of the vocabulary is needed to predict the next word. I think it's also an interesting effect. Okay, that was for the RNNs. So the current neural networks are quite specific if we're talking about Bayesian neural networks. The next step, we're talking about structure classification. I remind you that it is when we zero out all the outgoing weights from one neuron. So we can, as a result, we can remove neurons because they are like useless. And it can also speed up the forward pass. It's our desire too. So how can we do it in Bayesian approach? Actually, it's a very, very simple idea. Again, there are a lot of simple ideas. So this is the formula for our forward pass. Previously, we had like B equals W times A, or reverse. Here we change the notation, so x2 equals sigmoid of Wx1 plus B. And we want to obtain structure classification. We just introduce these group variables Z, they are in the blue, and perform element-wise multiplication. Let's see what happens here. We will treat this Z in the same way, almost the same way as our weights. So we will sparsify the components of this vector Z. And for example, we choose one component of this vector, for example, like any of the crossed one. And if this component in Z is 0, then X, the corresponding component in X, can always multiply it by 0. So it's like a useless neuron. It doesn't affect the network output. So this is a very simple idea. We just modify our computational graph a bit, but it results in structure sparsity. And how we will train this Z? We will do all the same thing as with W. So we put log uniform prior, normal approximate posterior, everything fully factorized, and so on. The only modification is that for Z we don't need local reparameterization trick, because something is already efficient. Because Z is not square, it's like one-dimensional vector. That's it. So very simple. Looks like a heuristic. However, for this model, it can be we can come with more mathematical motivation. Let's do it. But in here we will choose another prior. So previously we put the same prior. Here we will use standard normal prior. So our Z is like log uniform prior, and for W individual weights, we call them individual here. It's like standard normal prior. And since Z and W are independent in prior, we just, if we want to draw like probabilistic model, we just draw two separate circles. And this is our forward pass. And then we make an observation.
So when you say log uniform, you just invert it and take the log of it, and you like how does this P of Zi proportional to what you have? How do you do it practically?
As in sparsity, yes, you implement it right now. So it's like the same model.
Okay.
So the same prior, everything.
No, but it's still not very clear to me. So if we put the log, so the Zi comes to numerator, and we get a -1. So we simply sample from the normal distribution and we multiply it by -1 and we get this probability of
No, we don't sample from this distribution. We will sample from approximate posterior, and it is prior distribution.
okay, the same kind of thing that in this one.
But what we will do, we will like train the model. Then a lot of Z's will be like very noisy, And if they're very noisy, their mean becomes 0, and there will be a lot of 0 components in Z. So this is our model, and here we make an observation. It's again based on the properties of the normal distribution, that if we fix Z and then multiply W by Z, then we will know the distribution of this W multiplied by Z. It will be normal with variance Z squared. It's like the property of the normal distribution. And again, we can do another parameterization of the same thing. Let's look at it. So we denote this W times Z like tilde W, and it will be our another parameterization. So it's equivalent parameterization or model. So we take, let's look what happens here. We have now hierarchical prior. So we firstly sample Z, and then we sample tilde W based on that. So now our prior is hierarchical, these two things are dependent. But here we don't use Z in the computational graph, we have just tilde W. And why is it like good? Because here we make another observation, is that if we now find the marginal prior for tilde W, it's like this integral, we just end up in our usual log uniform prior. So actually this model is our sparsity model, but with the already induced structured sparsity because of our hierarchical prior. So it's a bit more mathematical motivation for this model, for this like multiplication on group rates. But practically it's very simple. So you just don't need all that stuff in practice. You just multiply by Z and do all the same things. And these are the results. I select only the one graph from the paper. It's about speed up of the forward pass. So here we can remove unnecessary neurons. So the width of our network becomes smaller, and that's why our forward pass becomes faster. Here on the left is CPU and right is GPU. The blue bar is for original uncompressed model. And then there are several models. So green is for baseline. It's group lasso-based approach. It's like magnitude pruning. And then pink is our model. It performs with worse, but there is a yellow model. It's from the same paper. It's Bayesian model, but with more complex like prior. So it actually speeds up really the network. Okay, and the next small part. I remind you at the beginning we were talking about two popular approaches for sparsification. The first is Bayesian pruning, Bayesian sparsification. The second is magnetic pruning. And magnetic pruning is just a simple heuristic approach based on lasso regularization usually. And it's interesting how they are compared, and also whether they work for large networks. And it was this paper this year, it's on archive now. They ran really a lot of experiments with these models on two large settings, with transformer network for machine translation and with ResNet 50 for ImageNet. These are large data sets, quite a big data sets, okay, and the big network. And they tried a lot of hyperparameters for both methods, just to compare them fairly. And it was like thousands of experiments on GPU. It's like amazing. Do you have such a lot of GPU? Me not. Okay, these are hyperparameters that tried. So for sparsity, remember I told you that we don't have hyperparameters in sparsity, but if you want, you can introduce them. And this is what they do. So they try to tune k weight shadow, and also they tune sparsification threshold, but it is very cheap operation, as you remember. And hyperparameters for magnitude pruning, there are like target sparsity, so they set to 0 a portion of the weights. Starting an any iteration of iterative process sparsification, so they train, prune, retrain, and frequency of pruning steps. So they tried a lot of hyperparameters for both methods and compared two models. And here we have two metrics. It's like quality and sparsification, and they are like conflicting. So look at the bottom, at the picture at the bottom. Each point here represents one method with one hyperparameter configuration. Let's focus on the blue and the green ones because it's variational dropout and back pruning we are comparing. So they have a lot of like experiments. This line in violet color is the baseline quality. We see that for sparse model the quality is usually lower a bit, but yes it is. And on the top picture they just plot the line around all these dots. So it is easier to compare. And here we see that both frameworks perform relatively the same, as well as other approaches. For high sparsity level, magnitude pruning here outperforms a bit. Bayesian Sparsification, yes, but on the left, actually with less compression, L0 regularization outperforms, and it is also the Bayesian approach. And for ResNet, the same thing. So here we also have like sparse variational dropout in blue and magnitude pruning in green. Also there are lines. And here is the reverse situation that sparse VD outperforms magnitude pruning for high sparsity level. And again, the relative performance of both frameworks is the same, but actually, personally, I think that in magnitude pruning, there are really a lot of hyperparameters, and it's hard to deal with them because you need to do a lot of experiments to tune them. As I mentioned before, there are other classification models. So, for example, also mentioned yesterday, horseshoe prior. Here, remember we had in structure classification Z and V, W, and it was like hierarchical prior, 2 levels hierarchy. Here they have 3 levels hierarchy. Of course, these distributions are chosen in a way that all the computational problems can be dealt somehow, and this results in even better compression as we actually seen on the slides. So, another approach is L0 regularization. L0 regularizer is a sum, is like a number of non-zero weights. Of course, it's non-differentiable regularizer, so it's hard to deal with that. But they relax it, so it becomes somehow differentiable. And relaxation is based like on spike and slap prior and approximate posterior, and this is their model. So this slide is we are not diving into details. It's just to show that there are other models, maybe even more successful, maybe not, but there are a lot of also Bayesian models for sparsification. So that's it. This is the summary. We thought about sparsification. That is a really urgent industrial problem that is well solved using Bayesian approach. Bayesian sparsification relies on Bayesian neural networks that have a lot of other advantages other than sparsification, and you can use them in your practice. But to train the Bayesian neural network, you actually need to use some tricks because we do it on the computer, and we discussed the tricks. They're usually not so hard, and when you apply all these tricks, your method actually turns to be very simple. And it's good, I think, because the easier is the implementation, the wider the method is used. So it's a good thing. So thank you for your attention. All the slides are available online. If you want to complete the assignment, do it. If you have any questions, just feel free to send me questions in Telegram or WhatsApp. Thank you. And if there are any questions?
You can advertise some school.
Okay, we are holding the summer school on deep learning and Bayesian methods in Moscow at the end of August. Application this year is unfortunately already closed, but maybe next year. Thank you.